Okay, so let's talk about what we call equilibrium solutions and stability. So, the type of differential equation that's relevant here is called an autonomous one. And in particular, we're going to talk about first order autonomous differential equations. Autonomous just means that the differential equation doesn't really involve the independent variable. So here I would say x is the dependent variable and t is the independent variable. And when I say it doesn't involve the independent variable, it means, other than the fact that I see a dt down here, I don't see any other t's in the differential equation. So in general, you might have dx over dt is a function of both x and t, and what makes it autonomous is that it's not a function of both x and t, it's just x. Anyway, we've seen examples of such things now that we know what they're called. For example, Newton's law of cooling is an autonomous differential equation. So here our variables are big T and little t, and the rate of change of big T, which is temperature, is, there's a constant K involved, which is different according to like what medium you're in, whether it's air or water or whatever. But that's just a constant. And then the point is little t doesn't appear over here at all. And big A is the ambient temperature, which is also a constant. So this is an autonomous differential equation that we've seen before. And the one we talked about most recently, which is the logistic model for modeling population growth, is also autonomous. For this one, the differential equation had this form. K is a constant, M is also a constant. So the point is this right-hand side of this equation does not involve little t. That's what makes this autonomous. So I am going to switch over to Maple and show you some slope fields for these. Okay, so let me show you some slope fields for autonomous differential equations. So I'm using Maple. This is software that it's available in the library and I think other computers on campus. But so I'm not going to explain everything, but maybe I'll walk you through it just a little bit, just because I don't just want to show you these pictures. So this is me declaring a package. This has certain tools that I would not be able to use unless I declare this package first. In particular, all this stuff in blue is a list of new functions I can use uh, once I declare this package. And not that this matters too much, but here's the one I'm about to use. D-field plot. That's what I am about to use right down here. And this is just the command to draw a slope field. So this first one is Newton's law of cooling, or it's a specific example of it. So Newton's law of cooling says derivative of temperature with respect to time. So that's like the derivative of big T with respect to little t. And by the way, this says T prime. The apostrophe doesn't show up too well, but okay, there we go. I highlighted it. So that's T prime of T equals negative K, and I just put in 1 for K, times T minus A, and I just put in 3 for A. So this is like Newton's law of cooling if the ambient temperature is 3 degrees. I just chose 3 because I wanted the picture I didn't want to use too big of a number, so the picture looks reasonable. Um, and this other stuff is just choosing the window. So like little t is the horizontal axis and big T is the vertical axis. So this information is just choosing the window. Uh, this is telling me like what these little line segments will look like, and that there's different options to make the picture look different, but I just chose simple little red line segments, and then that's essentially what this is saying. And then this last piece of information is telling me, or like that's how I tell it, like the density of these arrows. And 30 by 30 means that there's 30 arrows going from top to bottom and 30 from left to right. And so this is a slope field of the differential equation that I put in. And Of course, this is an autonomous differential equation. So the differential equation has no dependence on little t, meaning that it makes sense that as I scan from left to right, if I look at any horizontal section, what I see is the same slope over and over again. If I scan vertically, then I see different slopes, but if I scan horizontally, it's always the same. And so today we're talking about the behavior of the solutions of these differential equations. Of course, if big T equals 3, then you plug it in and you get T prime equals 0. So we see a horizontal line at big T equals 3. And I tried to make it so, of course, the where I'm scanning across is not quite big T equals 3. This is like big T is a little bit less than 3. So we actually see a tiny, tiny positive slope. These are not quite perfectly horizontal, but it's close to 3 and it's close to horizontal. I tried to make it as close as I could by adjusting these numbers, but I couldn't quite. Well, maybe I gave up too early, so I didn't quite get it to look perfectly horizontal, but that's okay. So right. One thing that we notice from here, which this makes intuitive sense, this is why I like the example of Newton's law of cooling, is of course, if our object is below the ambient temperature, then the object is just going to heat up until it's closer and closer to the ambient temperature. So we can imagine if I'm starting down here and I just follow where these lines go and I go with the flow, as I go from left to right, I'm approaching this horizontal asymptote of 3. But likewise, if instead of starting out below the ambient temperature, I start out above the ambient temperature, so I'm going to put my cursor, say, up here above 3, then I mean, intuitively, the object is going to cool down until it's again closer and closer to the ambient temperature. And similarly, so I can scan from left to right. And if I just follow the directions of these slopes, I find myself drawn towards uh, big T equals 3 again. Anyway, what we have down here is an example of the logistic model. So this was like P prime equals K times P. So I just chose a number for K times M minus P. So I just chose a number for M. And similarly, I put in information for what I want the window to be, and this other information is the same as it was above. And so we have a new slope field. Typically, for logistic equations, typically we focus on the situation because P is population. We don't consider there to be a negative population. So it should be positive, and typically we consider it to be smaller than M. So M is 3. So typically we would be in a situation where I'm from here to here. Here's 0, here's 3. Uh, and if I start anywhere in between, I can see that it's going to be slowly increasing. If I just sort of go with the flow and follow the directions of these lines, I find myself approaching 3 again. Of course, it does make sense to consider values of P that are above M. Like we call M the maximum capacity. That's because it's not really possible to sustain a population above M. However, you could start out with a population above M, and so if I imagine my cursor up here, it is going to decrease. It's going to go down towards M because M is the maximum sustainable amount. Uh, of course, like I said, we don't really like if P is population, we would never consider a negative population. But just for fun, let's imagine that, well, let's forget that P is population. Just imagine that P is some function that satisfies this differential equation and is allowed to be negative. If I start out P, whoops, if I start out P as a negative number, like wherever my cursor is here, it's going to move away from, yeah, like it's going to become even more negative. and sort of go down sharply like this. So, right, what we're talking about today is stability. So, if the population is exactly zero, then it's going to stay at zero. Like we have horizontal lines right here. It's just going to stay right where it is. Also, if the population was exactly three, because of this factor, that like this would tell me p prime is zero if p is three. So it would likewise stay at exactly three. And those are called the equilibrium solutions. It's like constant values where p will stay forever if it starts out there. And they can be either stable or unstable, roughly speaking. Stable means, here, I'll look at this equilibrium solution, p equals 3 up here. I would describe this as stable, roughly speaking, because if I'm a little bit above there, then the differential equation just tells me to go back down towards the equilibrium. And if I'm a little bit below there, then the differential equation again tells me to go towards the equilibrium. The idea is basically, math is perfect, but real life has noise and real life is fuzzy and real life has errors in it. Roughly speaking, I would say stable means if there were like a little bit of noise that pushed you away from the equilibrium, like say you were right at the equilibrium point, but then something bumped you a little bit up or a little bit down. Stable means that the differential equation would push you back towards where you were at the equilibrium point. So p equals 3, this is a stable equilibrium. P equals 0 down here, I would say is unstable because if I'm a little bit above 0, then like these slopes are positive, so it's going to push me even farther away from 0. And likewise, if I'm a little bit below 0, then these lines will push me even farther away from 0. So if I'm like perfectly at 0 and then something bumps me a little bit up, then the differential equation is just going to carry me even farther and farther away instead of pushing me back to where I was. Or if like something pushes me down, then the differential equation is going to make me keep going that way. Okay, so going back to an autonomous differential equation like this, an equilibrium solution is just a solution where x of t is a constant, and it should be a constant where f is 0. Because, of course, if x is a constant, then the derivative is 0, and f is 0, so the differential equation is satisfied. 0 equals 0. And so such a value c, we often call it a critical point. I'm going to pretty much use the words critical point and equilibrium solution interchangeably. So let's talk about what a phase diagram is. I'm going to draw an example, so let me just tell you what it is in words. It's a number line that we're going to break into intervals where f is always the same sign, either positive or negative. So there's going to be intervals where f is always positive and intervals where f is always negative, and it's essentially a number line that tells you which is which. And here's how we label it. We put an arrow pointing to the right, and that indicates that f is positive, and an arrow to the left indicates that f is negative. Why is that? On a number line, right is the increasing direction, left is the decreasing direction, and that perfectly corresponds to what the differential equation is telling us. If f is positive, then x should be increasing, because that means the derivative of x is positive. That means increasing, so we draw an arrow to the right, increasing, and vice versa for the left. So, how you can recognize a stable equilibrium or an unstable equilibrium is you look at the corresponding critical point C on the number line, And imagine that on your number line, these intervals are filled in with left arrows or right arrows, indicating that x is either increasing or decreasing when it's in that interval. If you see two arrows pointing towards your critical point, then it's stable. That means, and again, this is like the same thing that the slope field was telling us, that if I'm a little bit off of the critical point, that it's just going to push me back towards the critical point, no matter which side I am on the critical point. If I drift a little bit away from it, the differential equation tells me to go back towards it. Unstable is any other situation. Typically, in unstable equilibrium, you'll see both arrows pointing away. However, there's plenty of examples where one arrow points towards C and the other one points away. By the way, we're going to call all of these unstable. Some people call these semi-stable because, and there's a reason for that. I'm not really going to use that phrase except for right now, just to explain. I mean, it's in a way, it's halfway stable, right? Like if I were to drift to the left, then I would be pushed back towards the right. But if I drift towards the right, then I'm just going to go to the right forever. Or likewise over here. This one, things are switched, but it's sort of like stable from one side. That's why some people call it semi-stable. But we're not going to be that articulate in this class. I'm going to call all of these unstable. So the only one I call stable is like this. Anything else is unstable. So let's do a concrete example. So we're going to find equilibrium solutions for this autonomous differential equation and state whether each one is stable or unstable. So this is my f of x. I want to find my critical points, which are values that make this 0. So I'm going to set this equal to 0 and solve for x. And so we can factor this. 0 to -2. Those are my critical points. Let me actually, I'm just going to write that. Okay. Let's start drawing our phase diagram. I'm going to mark my critical points. There I go. So these are the spots where f is 0, and in between, or maybe I shouldn't say in between, but everywhere else, like to the left of -2, and then in between -2 and 0, and so on, I'm going to label each one of those intervals with an arrow, either pointing to the left or right, indicating whether f is positive or negative. And so I can look back at my work and tell this. All I care for this is whether f is positive or negative. If I'm plugging in a value less than -2, then this is going to be negative, this is going to be negative, and this is going to be negative if I'm plugging in a value less than -2. So I'm going to have negative times negative times negative, which is, which is negative. So negative means point to the left. In between here, x is negative, x minus 2 is also negative, but x plus 2 would be positive if I'm plugging in a value that's, like, I could imagine x is just -1, for example. So summarizing again, I would have negative times positive when I'm in this interval. So arrow points to the right. Here, I can imagine x is 1. This is going to be positive, negative, positive, which is negative. That points to the left. And then finally, over here, I can imagine x is 3, positive, positive, positive. Everything's positive. Goes like this. Okay. Let's say whether they're stable. The only situation I call stable is both arrows pointing in. -2 is not stable. Both arrows point away. 0, stable. 2, unstable.